Thank you. What a wonderful crowd. Looking around the room, see a few faces that look like you guys remember a time when the solar system had 9 planets, right? Before the demotion of Pluto to dwarf planetary status back in 2006. How many people are still Pluto fans, by the way? How many people? Okay, a lot of Pluto fans. Okay, a lot of people yearning for the glory days of the 9-planet solar system. But you don't have to worry, because right here, right now, we're going to restore the solar system to its former 9-planet status, make the solar system great again. Are you with me? There's parts of America where this joke gets even a bigger response. Yeah. So the remarkable thing about solar system astronomy, and particularly planetary solar system astronomy, is that as an endeavor, it has been highly inefficient. Okay, we have discovered, since Galileo's invention of the telescope some 400 years ago, only 2 bona fide planets, right? The first one was discovered in the year 1781. Okay? It was discovered by an astronomer by the name of William Herschel. He worked for King George. And his job was very simple. Well, simple, not easy, right? He would just scan the night skies every night, would draw what he saw. Now, one night, he noticed that the place where he drew a particularly dim star was slightly different than where he drew it the night before. He went back the next night, it had moved again. He realized almost right away that this dim object that was moving very slowly across the night sky was not just an asteroid, it was not just a comet, it was a legitimate, distant planet. Okay, so this is how the 7th planet in the solar system was discovered, because after all, everything out to Saturn, right? So Mercury, Venus, of course, Earth, Mars, Jupiter, and Saturn, you can just see with your naked eye. So these 6 planets were known to the ancient civilizations, and the first planet in the solar system that was truly discovered astronomically was not found until the late 1700s. So what mathematicians realized right away after this discovery is that if you track this motion of this tiny distant planet, you can go back to journals of astronomers from the past and reconstruct its orbit. Okay, so very quickly, the orbit of this planet was reconstructed, and immediately they noticed that something was horribly wrong. Okay, and this was really put together into a nice set of tables, right? The fact that the reconstruction of the orbit, right, was beautifully reconstructed by Alexis Bouvard. He was the director of the Paris Observatory, which is less than 2 miles away from here. He put together this manuscript in 1821, where he pointed out that something is horribly wrong. This planet, okay, Uranus, is deviating away from where it's supposed to be. Right? Night after night, okay, month after month, year after year, it was the error between where it was supposed to be theoretically and where it was growing. And you can see that very clearly from this slide, okay? Because you have like some sines and cosines over here, you have a table. Uranus is not where it's supposed to be. And actually, my French is terrible, okay? But kind of what I'm told is going on over here is that Bouvard, being a good theoretician, it proposes 2 solutions. He says, number 1, maybe we shouldn't trust the data, okay? Because after all, it's just like astronomers looking at the sky. How precise can that be? So that's option 1. But he says, on the off chance that the data are right, we cannot rule out the possibility that what's going on in the distant solar system is that there exists yet another planet beyond Uranus, which is gravitationally pulling on and causing it to go off course. So this was 1821. The promise of this data set didn't really come to fruition for a couple decades, and the man that is credited with the mathematical discovery of this extra distant planet is Urbain Le Verrier, who also spent his life working at the Paris Observatory in close proximity to us. Now, Leverrier has always been an inspiration to me. Did my undergraduate thesis on the extension, on kind of the long-term extension of his work. But something that I've kind of learned to do when I was an undergraduate, well, because I didn't have any money, so I was living in a crappy apartment in Santa Cruz, in a bad part of town. So I learned how to spot a gangster. Okay, like you can look at Leverrier, it's a gangster. Okay, you can tell because he's got the bling like on the outside, right? His stage name is Urban Leverrier. So we're surrounded here with great art, and in the Louvre, and I've been told that sometimes artists take like some liberties with how they paint people. So I did my best to reconstruct what Leverrier actually looked like, and I think it was like this. I think it was kind of a thug. You too, by the way, can download the Thug Life app on your phone, okay, and do this in your free time. It's fun. So here's a page out of Leverrier's manuscript detailing the calculations of how he was able to predict mathematically the existence of the planet Neptune, right? He was able to derive both its mass, its orbit, and its location on the night sky from the deviation of the orbital trajectory of Uranus. As it turns out, this story is really, really remarkable. When he was done with his calculations in 1846, he came, of course, to give a talk to the observing astronomers. So he was a theoretician, a mathematician, essentially, and he tried to convince the observers to go and find this elusive planet that he had calculated. And this was done here in Paris. It was very warmly received, right? For example, Airy was a very famous geophysicist at the time, said, "I cannot attempt to convey the impression which was made on me by the author's undoubting confidence, but the firmness with which he proclaimed to the observing astronomers, 'Look into the place which I have indicated, and you will see the planet well.'" So Leverrier was convinced that his calculations were right. And they were right. But as it turns out, they were only right because of timing. Okay? So as it turns out, science is just like show business. You got to be at the right place at the right time, making the right predictions. And the fact that this was all happening in 1846 played a tremendous role. Why? As it turns out, Leverrier and his contemporary, Adams, who was doing a similar calculation in Cambridge, both got the mass and orbit of Neptune slightly wrong. Right? So here's the real orbit of Neptune. This is where it was in 1846. These are their predicted orbits. You can see they're somewhat more elliptical, somewhat larger, okay? But what they got correct was the location of Neptune in the night sky. As it turns out, in 1846, Uranus and Neptune were suffering a conjunction, so that data was readily available. So even though they got the orbit kind of wrong, they got the location in the sky right. So Neptune has been around the sun since this time almost exactly once. It goes around the sun 164 years. And if you were to redo this calculation in 2011, when Neptune was back to where it had started, both Leverrier and Adams would have gotten the wrong answer, right, on the sky, even though they would have correctly predicted the existence of Neptune. So I find this to be a remarkable story of both kind of mathematical genius and coincidence working out in favor. So I'm not the first person, of course, to notice this. There was a hipster from Cambridge, Massachusetts, named Benjamin Pierce, who said Leverrier's calculation was nothing but a happy accident. And he kind of inspired, he said this could be repeated multiple times. Now that we found Neptune with mathematics, we can look for more planets beyond Neptune this way. And he inspired Parzival Lowell, who came from a rather wealthy family in Massachusetts, to go out and look for more objects, okay, using mathematics. So Lowell actually was not a good mathematician, not a particularly good astronomer either, but he did have like the Ford planned mentality. So what he did was he hired a bunch of mathematicians to do calculations for him in a very kind of production line sense, and built the Lowell Observatory, which still is going pretty strong today in Arizona, to look for this next planet that he called Planet X. So Lowell then suddenly died in 1916, not having found this object. But the search for Planet X, the planet beyond Neptune, continued. And eventually it was found. It was found by this guy, Clyde Tombaugh. Here's a real picture of him. His biography also can be purchased in children's book format, which I prefer, much more tangible. So Clyde Tombaugh, who was employed at the observatory, just went and found it in 1930. It was a huge deal. Okay, this is the Sunday edition of the New York Times. Right above the fold, you can see right here, it says, "Astronomers hail finding." Right, the sphere, possibly larger than Jupiter. And remember, Jupiter is the biggest planet in the solar system, 316 Earth masses, right? And 4 billion miles away, meets predictions. So Leverrier's miracle has been done again. As it turns out, this was not Planet X at all. It was Pluto. What they found was Pluto. They initially mistook Pluto for something much, much bigger, because according to the calculations that Lowell had, Pluto was supposed to have a mass of about 7 Earth masses. But as continued observations refined the mass of Pluto, people eventually realized that Pluto is tiny. It is a few thousandths of an Earth mass. This is why it's not a planet. Okay, by the way, Pluto, there's remarkable similarities between Pluto and Russia. They're both very cold, first of all, but the surface area of Pluto is actually almost exactly equal to that of Russia. And both kind of exert remarkable influence on social media, particularly Twitter. It's true. So it so remains that since 1846, no actual planets have been found in the solar system. And that was the last time we found something big. So for a long time, Neptune was considered to be the end of the solar system, and Pluto was considered to be kind of a small rock that's orbiting beyond it. Here's the orbits of the solar system from the top down. We have Jupiter, Saturn, Uranus, Neptune. This blue thing is the orbit of Pluto. What astronomers did find, however, in the last 30 years, is the existence of something called the Kuiper belt, a second asteroid belt in the solar system, which we didn't know about until the mid-90s. So here, all of the objects with well-determined orbits in the Kuiper belt. As you can see, it's not really a belt, it's more of a donut. It's got this vertical structure, which is very interesting. And each one of these bodies is quite small, right? They're no bigger than Paris on average, right? So their cumulative mass is actually very, very low. It's only about 1% of that of the Earth, which is negligible. But their dynamical structure, right, their orbital structure of this belt is really interesting, and it's been a remarkable revolution in our understanding of how the solar system formed since the discovery of the Kuiper belt. I'm not going to dwell on that too much right now. All that I want you guys to notice for now is that it looks like just all the orbits hug the orbit of Neptune. Right? You see how most of them are confined to this ring, but when they come to the closest approach, it looks like they physically touch the orbit of Neptune. There's a simple explanation for why that is. It's because all of these icy asteroids were thrown into their current neighborhood by scattering off of Neptune. Right? Neptune's gravity tossed them out. Right? And gravity is a conservative force. It's nothing to do with its political affiliation. Conservative force means when you go somewhere, you come back to where you started. Okay? So all of these orbits, even though they evolve in interesting and chaotic ways, they remain gravitationally tethered to the orbit of Neptune. That's kind of a rule of thumb, if you will, of the structure of the Kuiper belt. And for a long time, there weren't objects that violated this rule. Until about 2004, when Mike Brown, who is my partner in crime on this work, discovered the object Sedna. So you don't have to be like an expert in solar system astronomy by any account to note that something is different a little bit about Sedna, right? Something is horribly wrong, right? This orbit at its furthest point, right, goes out to 1,000 times the distance between the sun and the Earth, right? This is a huge scale, right? This is not a regular member of the Kuiper belt. But what I would argue is that the fact that it's so elliptical is not that weird. What's weird is that it's not elliptical enough, okay? The weirdest thing about Sedna is not that it goes out to a far region of the solar system. It's that at closest approach to the sun, it doesn't hug the orbit of Neptune. What does that mean? That means this object could not have been emplaced into its current orbit through interactions with the planets that we know of alone, right? Some other gravitational influence was needed to pull out the closest approach of this orbit, to stretch it. Yeah? So, generically speaking, in astrophysics, when you have one object, one data point that doesn't match the pattern, the explanation for it typically goes like this. People say, well, this Sedna, something bad happened to it a long time ago, 4 billion years ago, stars and stuff were flying, I don't know, something bad happened to Sedna. Okay, that was the explanation. But then, okay, a few years later, in 2014, Joe Biden was found orbiting the solar system, okay, on a trajectory very similar to that of Sedna, okay? And this was not, we actually didn't find it. This was found by Chad Trujillo and Scott Shepard, two different astronomers. And this discovery was actually the inspiration to do the work that eventually led to the Planet 9 hypothesis. The key thing that I want you to notice is that this object, which was nicknamed Joe Biden because when you discover an object in the solar system, there's this license plate that gets attached to it, and the license plate of this one was 2012 VP113, okay? So astronomers are actually not that good at jokes, right? So, right, you can see the fact that Joe Biden also, at closest approach, doesn't hug the orbit of Neptune. Some other gravitational influence is needed. So Mike Brown, my colleague, and I thought, okay, well, what's going on over here? Let's look into this much more closely. And something that we immediately found is that if you just concentrate on the most distant orbits that we know of in the solar system, they all swing out into the same direction, right? I mean, this is simple, and I'm surprised that we were the first people to really notice this precise alignment. You can see that they're all kind of in the same plane, right, which is tilted with respect to the plane of the solar system by about 20 degrees. They're all pointing into the same direction, right? You might say, okay, well, so what? Okay, so what? Well, as it turns out, if you were to leave the distant solar system alone in this state on a geologically short time scale, 100 million years or so, right, this pattern would disperse. The orbits would randomize. Right? The fact that they're all still pointing into the same direction means that there's some distant gravitational pull which is keeping them confined. Okay? So this was really the origin, the first piece of the puzzle. Right? How do we explain both the fact that the orbits of Sedna and Joe Biden are detached from Neptune, and why are they all pointing into the same direction? Right? Well, this is just a quote from my favorite film of all time, right? Strange things are afoot in the distant solar system. Okay, so you can go and do some calculations, right? Inspired by very much same type of theories as what Leverrier developed in the 1800s here in Paris. And I would like to really thank the organizers for allowing me to take the next 48 minutes to discuss this slide. You know, it's a dear slide to me. No, I'm kidding. By the way, I gave like a variant of this talk at a math department one time, and people said, stop, all your other slides are bad, this one is good, let's talk about this one. Okay, so what you can do is you can kind of write down equations which stem from something called perturbation theory. This doesn't give you the exact answer, but what it tells you is that if this source of gravitational pull comes from a distant planet, right, a yet undiscovered planet in the solar system, then the planet must have a mass which exceeds that of Earth by a factor of a few. Right? This can't be a small thing. This can't be another Pluto. This has to be a super Earth. And as dramatically, its orbit can't be a circle. Right? Most planets in the solar system just go around on kind of circular orbits. This one has to be different. Its orbit has to be appreciably elliptic. So the advantage of living in today's world as opposed to the 1800s is that we have vast computational resources available to us, and I think I should here give credit where it's due. Caltech, the organization where I work, it kind of prides itself on giving support to kind of crazy ideas. So when we came and said we would like to take over our division's entire computational resources for a couple of weeks because we think there's a planet in the distant solar system, they said, yeah, you should, yeah, go ahead. So this is what we came up with, right? We actually ran thousands of these simulations. These simulations are long-term evolutions, like synthetic long-term evolutions of the solar system over its dramatic lifetime. They start out 4.5 billion years ago when the Kuiper belt, this field of icy debris beyond Neptune, was first scattered out. Okay, so it's represented as this kind of mishmash, unorganized, right, set of highly elliptic orbits. And we run time forward, okay, introducing both the gravity of the planets that we know of, which are confined to right here. This is, for scale, the orbit of Neptune. This is 30 times the distance between the Earth and the Sun. By the way, if you look very closely over here, you'll see the Earth. Actually, my house is over there. You can see it. And then what we allow the system to do is to evolve self-consistently. I apologize for this technical hiccup here. And just kind of the gravitational and body evolution to unfold. So what we see in time, okay, and we're about 2 billion years into the solar system's lifetime at the moment, is that in time, orbits that started out pointing into the same direction as Planet 9, which is shown here as this big pink ellipse, disappear from the system. What happened to them? Actually, they've been kicked out into the interstellar medium. They've left the solar system, never coming back. But the orbits that survive are ones that are predominantly, okay, confined to looking the opposite direction, right? And by the way, you guys see this too, right? I'm not alone in it's okay. Then the theory's right. Yeah, so it took actually a while to understand why they're anti-aligned instead of aligned. There's a complicated reason for why, but we kind of understand it now. But one of the remarkable things about this discovery, that introducing a planet on an elliptic orbit, which is a few Earth masses into the distant solar system, both explains why the orbits are confined together and how their orbits get detached from Neptune, because as they rattle around in here, right, their orbits grow less and more elliptic in time. So you can kind of see the cycling of regular Kuiper belt objects becoming objects like Sedna and Joe Biden, then going back to being garden variety Kuiper belt objects. So the solar system, the distant solar system, is in this mode of breathing with sort of a 500 million year life cycle where the orbits are constantly expanding and contracting and changing their shape. So if you kind of put all of these things together and match the simulations back to the observations, what you will discover is that the data are best explained by a 5 Earth mass Planet 9, which resides on an orbit that takes about 10,000 years to go around the sun once, and has an orbital ellipticity out of roundness of about 30%. Okay. So that's the answer. And for this theory, I assign us a B+. Okay? Right? I mean, I have to be, I can't be hypocritical. I always tell my graduate students that if you have some model, right, that successfully explains the data that you're trying to explain, you will get a B+. Why not an A? It's not just because nobody's perfect, right? You don't get an A because a theory that merely explains what you know hasn't predicted anything, right? In order to get an A+, you have to make a prediction and then go out to the sky and measure it to see if it's true, okay? And then decide if it's right or wrong. In this sense, by the way, Einstein's theory of general relativity gets like an A++, right? He's made predictions that weren't confirmed until 100 years after the theory was formulated. So that's the way to go forward. And so we looked for a while for what was special about Planet 9, right? What was it that we were making in the solar system that wasn't yet observed? And the answer is right here, okay? Now, my former graduate student, Chris Spalding, has advised me to never show this plot. Okay, he says it looks really bad. It looks at best like modern art, and like not good modern art, like bad modern art. But I like it anyway, because the key thing here is the y-axis. Okay, what the y-axis shows is in degrees the orbital tilt, right, with respect to the plane of the solar system of the Kuiper belt objects in our simulations. So there's a bunch of stuff hanging out close to 0. Okay, these are objects that are kind of living close to the solar system. But what the model also predicts is the distinct existence of objects that take this really complicated dynamical ride where their orbits flip upside down and then they come back, and they should follow a path like that. Okay, and we thought, this really is something, right? This is a prediction. We don't know of objects in the solar system that are orbiting upside down, right? So this would be a remarkable prediction to make. And then we went and looked in the data, okay, and we found some, okay, and they all fell right here. These were the first 5 objects that were kind of the first hint to this population, which is unique to the predictions of Planet 9. As it turns out, in physical space, they look really crazy. They look like these long, really distant wings of the solar system on which it flies at you. So, I don't know. For me, this line of evidence for the existence of Planet 9 is actually my favorite. Maybe it's not necessarily the strongest, but it is my favorite because it's not something that we initially set out to look, right? It came out of the calculations, and it turned out to be true. And since then, the data set has kind of expanded by about a factor of 2. We now know of quite a few of these objects. So I think this is a remarkable smoking gun for the existence of Planet 9. Okay, after we published all this, well, I was out on a run, just doing my thing. And then I got a call from a friend of mine who's a reporter who said, okay, this is a huge, huge story. Okay, astronomers have found an object which is orbiting the solar system upside down. What is your take on this? Like, what is your comment? And I was on my run. I said, okay, I will tell you exactly what happened to this object. And then I told her the same exact story I just said. Now I said, well, Planet 9, it takes these really distant objects, and then it flips them upside down. They're these really extended, like, wings of the solar system, blah, 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 blah. And she said, okay. Then when I got back to my office, I looked at what the object's orbit was. It was nothing like what I had imagined, right? It was just completely wrong, right? In fact, it was an object on a perpendicular orbit to the solar system, right? Living immediately outside of Neptune, okay? Where Planet 9's gravity doesn't exert a strong influence. And I was just like, oh man, it's kind of embarrassing. But then Then I realized something. I realized in those simulations, in those calculations that I showed you a few slides ago, I said there are all these bodies that disappeared, right? They left the solar system. Well, many of them did leave the solar system, but actually some of them disappeared from the screen because they got scattered in. Because ultimately, Planet 9's gravity doesn't care about a sense of direction, right? It doesn't know, okay, that way is out of the solar system, this way is in, right? It's just scattering every which way. So I decided to go back and re-examine, okay, what the evolutions look like of some of the objects that got scattered in. Okay, and here's what we found. Okay, it's remarkable, right? So again, right here are the orbits of Uranus and Neptune, these pink circles. Okay, this is the orbit of Planet 9. This is just a simulated synthetic Kuiper belt object dancing around in our computer simulation. And what you see is that every time it comes to hug the orbit of Neptune, it gets perturbed, right? It gets scattered in. And in time, okay, it gets scattered in until it parks itself onto this perpendicular orbit, which was just like this new object that was discovered in the solar system. And at this moment, I realized that if you liked it, then you should have put a ring on it. I mean, that's what that song's about, right? This is just the astrophysical context of Beyoncé is remarkable. Okay, so today, right, we think we know the orbit of Planet 9 actually pretty well. This is what the data set looks like at the moment, right? You see that there's a lot more objects that have been discovered in this cluster, long period bodies. There's a few interlopers as well, which is, I mean, it was worrying me for a long time because we see these in the simulations, and in the original data we didn't see any, so I was worried about there being something wrong there, but they do exist. And as I mentioned, the best fit for Planet 9 is a 5 Earth mass object on an orbit of 10,000 years around the star. Now, we don't have an equivalent of a 5 Earth mass object in the solar system. We go from Earth, which is one. Turns out the Earth is 1 Earth mass. Okay, then the next one is Uranus and Neptune. Both of them are 17. Okay, and then we go to Saturn and Jupiter, which are 90 and 300 respectively. Okay, but we don't have an equivalent for a 5 Earth mass object. We don't actually know what that looks like. What's remarkable is it turns out 5 Earth mass objects are the most common type of extrasolar planets that we find. So around other stars, we haven't found Earth equivalents, right? There's some things that are kind of 2 Earth masses. They're giant planets like Jupiter and Saturn are very rare. As it turns out, the most common type of outcome of planet formation is a 5 Earth mass object. I mean, it's just true. So I think Planet 9 is kind of the missing link of the solar system's planet formation process, right? And when we see it, when we get images of it, it will be really interesting to see what this object looks like. So what are we doing to bring you actual photographs of Planet 9? Because after all, for now, all we have is gravitational evidence, right? We're right now in kind of the same state as Leverrier was before Neptune was discovered observationally. Right? Well, we're conducting a kind of a large-scale search using this telescope right here. This is the top of Mauna Kea on the Big Island of Hawaii. So we go to this guy right here. This is the Subaru telescope. The Subaru telescope is the National Observatory of Japan. It is the right machine for the job. And we do something very simple. We do what Herschel did. We take a picture of the night sky, and of course we take many, and then we go back the next night and we do the same thing to try and find that slow-moving, distant spot of light. The telescope itself is quite remarkable. This is what it looks like. For scale, this is me, and this is my friend Mike. Right, so this is just, you have to see it to genuinely appreciate the technological scale of this thing. But you guys have been so kind to me at this event, and it's just like been so much fun that I figured we'll just skip. Okay, we'll just skip this process, and I'll just tell you guys where Planet 9 is right now. Okay, so Planet 9 is right there. Okay, yeah. In all reality, it's actually somewhere in like this region, right? I think that's the most probable region for the location of Planet 9. So my hope is that on a time scale much, much less than a decade, right, we'll be back to a full-fledged 9-planet solar system. Okay, thank you for your time.